Now, starting off with last week, just to kind of go and recap, you had Brendan, he introduced you to the principles of refrigeration, you introduced yourselves to each other, and we looked at this basic principles here. So just to kind of remind ourselves, refrigeration, air conditioning, they all kind of work on the principles of the vapor compression, principle of vapor compression. So effectively what that means is that we have four main components: compressor, condenser, metering device, evaporator. So evaporator and condenser are heat exchangers. If you're involved in split air conditioning unit, you'll often hear people saying that this is the outdoor unit and this is the indoor unit. And that's because we have what's known as a reverse cycle system. And the reverse cycle system means that we can swap this outdoor unit to act as an evaporator and this indoor unit to act as a condenser. But effectively what we have to remember is that in order for a vapor compression system to work, you need to have two heat exchangers, and one heat exchanger effectively absorbs heat, which is the evaporator in this case, and the other heat exchanger rejects heat, which is the condenser in this case. So when you have an air conditioning unit and you put it on heating mode, the heat is being rejected into the room. When you have a air conditioning system and you put it on cooling mode, the heat is being rejected outside to atmosphere. When we're looking at refrigeration systems, so your refrigerated cabinets, your beer coolers, any commercial refrigeration system, even water chillers, effectively what we're trying to do is absorb heat from one area and dump the heat in another area. So when I talk about the evaporator is the heat exchanger that absorbs the heat. And when I talk about the condenser is the heat exchanger that rejects the heat. And we just need to remember that sometimes, depending on the type of equipment, that these two heat exchangers will take up different names, like heat collectors and plate heat exchangers and shell and tube condensers and shell and tube evaporators and so on. And we just get, over time, we will become familiar with the terminology. But effectively what we need to remember is that we have a compressor, we have a condenser, we have an evaporator, and we have a metering device. And they're the four main components. And everything else after that, so anything else that you see on a refrigeration plant or on an air conditioning system, they're accessories. They're what I would refer to as accessories, and they're there to make the system more energy efficient, or to allow us as service technicians to be able to access the system and carry out repairs. But they're not essential to the vapor compression system. However, once they're fitted to a system, they may cause problems for any of the main components. So what I mean by that is, for example, we have a compressor, and compressor's primary function is to take low pressure, low temperature, superheated vapor, so it draws it from the evaporator, and then it compresses it from a low temperature, low pressure superheated vapor to a high temperature, high pressure superheated vapor, and discharges it into the condenser. So it continues to suck and pump. So it pumps the vapor refrigerant, or pumps the refrigerant around the enclosed system. If I have an oil separator and an oil reservoir fitted, the purpose of an oil separator is to make sure that the oil is separated from the refrigerant and returned back to the compressor. And if I have a problem with the oil separator, that may cause the compressor to start pumping inefficiently. But it's not down to the problem with the compressor, it's down to the accessory that's been added on to ensure that oil is returned back to the compressor. But again, rather than confusing the issues, I'm just going to keep it simple for now. So we just remind ourselves, compressor pumps the refrigerant around the system. It converts the low pressure, low temperature superheated vapor to high pressure, high temperature superheated vapor. The condenser then, I called it 3 zones. As far as I'm concerned, there are 3 zones inside in a condenser. There is, first of all, the desuperheating zone. So what you will notice with when a refrigeration technician comes to a refrigeration plant, and they're trying to see if everything is working accordingly, when they're testing the condenser, they will put their hand on the top of the condenser. Now this comes with a warning, and the warning is that the top of the condenser could be as high as 70 degrees sensible temperature. So the temperature could be too hot to touch. So be careful when you touch the top of a condenser. The discharge pipe has high pressure, high temperature, superheated vapor. And if we just remind ourselves, when we're talking about superheat vapor, the definition for superheat is a vapor is said to be superheated when it's at any temperature above that of its saturation temperature. So maybe Brendan last week gave you an example of water. Water at atmospheric pressure will boil at 100 degrees Celsius. Any temperature above that, so any steam that you have above 100 degrees Celsius, so if you have 120 degrees steam temperature, then we have superheated vapor of 20 degrees. Again, we have to remember that pressure and temperature are related. So when your pressure is decreased, so will your temperature. So when we're dealing with refrigeration systems, because you've got high side pressure and low side pressure, we're actually changing the boiling temperature of the refrigerant on each side of the system. So the boiling temperature for the refrigerant in this condenser, for example, could be 35 degrees Celsius, and then you would have vapor superheated above that. Anything above 35 degrees Celsius is superheated vapor. Whereas on this side of the system, it could be as low as 5 degrees Celsius, again relating to pressure-temperature relationship. So the desuperheating zone is the first area in the condenser where you have high pressure, high temperature, superheated vapor, and that vapor has to be cooled down to saturation temperature, or boiling temperature if you like. So it has to go from 70 degrees down to 35 degrees before that refrigerant will start to change or condense from a vapor to a liquid. So after the first pass, you then enter in what I refer to as the condensing zone inside in the condenser. And the condensing zone is the area where the refrigerant, the vapor refrigerant, starts to change from a vapor to a liquid. And as it travels through the condenser, less and less vapor becomes present and more liquid becomes present, so that at a given point within the condenser, we have 100% liquid. When you have 100% liquid and that liquid is still being exposed, in this case if it's an air-cooled condenser, to the air, that air is actually a cooler temperature than the actual refrigerant that's circulating inside in the heat exchanger. Therefore, that liquid refrigerant, that 100% liquid refrigerant, now becomes cooled to a temperature lower than that of its saturation temperature. In other words, it becomes subcooled liquid or a subcooled liquid. So the last pass in your condenser is the subcooling zone. So just to recap, top part of your condenser, desuperheating zone. Middle part of your condenser, so these three passes here, if you like, are known as the condensing zone, and the last pass in your condenser is known as the subcooling zone. And then we have high pressure, high temperature, subcooled liquid exiting out of the condenser, traveling along the liquid line and going as far as the metering device. Now the metering device can be a capillary tube, it can be a thermostatic expansion valve, it can be an electronic expansion valve, and then there are other metering devices for different applications such as low side flow valves, high side flow valves, and then we also have low side separators and so on, which can act as a metering device. But a metering device is anything that will actually create a restriction, and by creating the restriction, it allows for, or it enables, a pressure drop. So metering devices control the flow rate of refrigerant into the actual evaporator, and metering devices create a pressure drop. So in other words, they reduce the high pressure, high temperature subcooled liquid to a low pressure, low temperature subcooled liquid. And what happens with the metering devices is we have a phenomenon which is referred to as flash gas. In other words, the act of creating a pressure drop means that the liquid will instantaneously boil off, and a certain amount of flash gas, in other words, a certain amount of vapor, is created. And this is often referred to as adiabatic expansion, whereby you've got instantaneous boiling off of liquid, and the actual temperature stays within the energy, or within the body of the fluid itself, so in this case the refrigerant, and that temperature isn't given off to the surrounding body. So in other words, the valve itself doesn't drop in temperature, doesn't change temperature. So the refrigerant itself will go from a high pressure, high temperature liquid to a low pressure, low temperature liquid, and there will be a small amount, or there will be a small amount of vapor. So in other words, we could find ourselves in a scenario where we have 90% liquid and a 10% vapor, and that's easier to show you when we go and use the pressure enthalpy chart. So I'll show you what I mean on a pressure enthalpy chart, that there is a small mix of vapor and liquid. That means then that we have to make sure that the temperature in the liquid line after it leaves the condenser is at a temperature lower than the saturation temperature of the refrigerant. In other words, that it's subcooled. And the reason for subcooling the liquid line is to make sure that we minimize the amount of flashing that takes place in the actual metering device, so that we maximize the amount of liquid that we have inside in the evaporator. And it's important because the more liquid you have in the evaporator, the more efficient the evaporator will be. So what we have to remember is that while the liquid in the evaporator is boiling off, it's changing from a liquid to a vapor, we are absorbing heat from the surrounding area. So wherever the heat exchanger is exposed to, it will absorb heat from the air or the water or whatever we're using that heat exchanger to absorb heat from, the medium if you like. So it will absorb the heat while it's changing from a liquid to a vapor. So as the liquid refrigerant travels through the evaporator, less and less liquid becomes present and more vapor becomes present, so that in a given point within the evaporator itself, you've got no more liquid and you've got 100% vapor. So when we get to 100% vapor, we're no longer absorbing heat, but what we are doing is that we are, because the vapor is still being exposed to the air temperature that's warmer than the refrigerant temperature, then what we're doing is we're superheating the vapor. In other words, we're still adding heat to the vapor, and that vapor then exits the evaporator as low pressure, low temperature, superheated vapor and returns back to the compressor. So a vapor compression cycle is a sealed system. The refrigerant should never leave the system. There's no reason for the refrigerant ever to escape from the system other than if mankind makes a mistake. So in other words, human error is the only reason why refrigerant will leave the system, or maybe it's deliberate that humans will deliberately allow the refrigerant to escape. But it's a sealed system, and if you maintain a refrigeration system, then there is no reason, if you maintain it properly, there is no reason for refrigerant to escape other than wear and tear because of poor maintenance, or other than human error because they put a hole in it or stood on pipework or did whatever. So poor maintenance, wear and tear, corrosion, that kind of stuff. But if you do a proper preventative maintenance routine on it, you will spot where possibly the potential for a leak can occur. And if you can do active maintenance on it, then you can save the refrigerant from escaping off to the atmosphere. So just to recap then, we have a high pressure, high temperature superheated vapor, exits the discharge of the compressor, enters into the condenser, desuperheats in the condenser, then it begins to condense from a high pressure, high temperature vapor to a high pressure, high temperature liquid. At a given point in the condenser, it then becomes 100% liquid, and then it continues to travel through the condenser and leave the condenser as a high pressure, high temperature subcooled liquid. It enters into what we refer to as the liquid line. So the pipe that connects the condenser to your metering device, and you will find on a refrigeration plant or refrigeration system, there will be additional accessories added, such as a dryer, a filter dryer, and a sight glass. They're the minimum. Then there can often be other accessories, but we just won't go there for the moment. But the liquid line carries the high pressure, high temperature subcooled liquid as far as the metering device. The metering device then creates a pressure drop. So at the exit of the metering device, you're going to have low pressure, low temperature liquid entering into the evaporator. And inside the evaporator, that low pressure, low temperature liquid starts to boil and change from a liquid to a vapor, so that at a given point inside in the evaporator, you have 100% vapor. That vapor is still exposed to the air coming across the evaporator, so it exits out of the evaporator as a low pressure, low temperature superheated vapor and returns back to the compressor, and the cycle starts again. It's important to note that superheat is a necessary evil, and it is built into a vapor compression system to protect the compressor so that the compressor doesn't have any liquid returning to it. Refrigeration compressors in the main are designed to pump vapor only. They don't pump liquid, and therefore the reason why we would have superheat inside in an evaporator, especially on commercial refrigeration plants, is for the very reason to protect the actual compressor from liquid getting back. So using a mechanical expansion device or metering device, so say for example if we use the thermostatic expansion valve, we set up a predetermined superheat value, and usually that's between 5 and 8 of a difference. So in other words, there's 5 and 8 degrees of a difference, and I'll explain that to you a little later on. And the reason for that, again, as we say, is because it takes a thermostatic or a mechanical expansion valve 15 to 20 minutes to react. So that's why we need to have that safety margin built in. On the other hand, with an electronic expansion valve, because we can get instantaneous reaction, then we can minimize the superheat value. So we can lower that superheat value because we can instantaneously shut down the solenoid, the electronic expansion device. We can shut it down within a split second, therefore allowing the liquid to boil off before it gets back to the actual compressor itself. And then when you're using things like a capillary tube, which you would normally find on a domestic system, we would ensure that there is what's known as a critical charge. So in other words, the exact amount of refrigerant that is required to remove the heat that we have calculated in the space that we're trying to cool is in the system, and not any extra and not any less. It's a critical charge, so we have to have the exact amount in it. And that all leads to what is referred to as balance points. So in other words, balance points means that the rate of compression, so the rate in which this compressor discharges the vapor into the condenser, is exactly equal to the rate of condensation. In other words, the rate at which this condenser will convert the vapor to a liquid, which is exactly equal to the rate of vaporization. In other words, the evaporator will then be fed liquid into it at the exact same rate that the evaporator changes that liquid from a liquid to a vapor. And then again, back to the rate of compression, the compressor will pull the resultant vapor from the evaporator at the exact same time that the vapor is being produced, and at the exact same time that the condenser is calling for the refrigerant to enter into it. So balance point basically means that when we size these components, we must make sure that if anything goes wrong, that we replace like with like, for example. Or if the condenser gets dirty, you're upsetting the balance point, and that's why you're not achieving temperature inside here. In other words, you're not absorbing the heat. What I'm trying to really get across to us tonight as well is that we have to remember, you do not produce cold, you do not make refrigeration. What we do is we absorb heat. So refrigeration or air conditioning or cooling is the process of absorbing heat. And then when we absorb that heat, we reject that heat in outside of the space that we're trying to absorb the heat from. These are the definitions that we all went through. And again, we have our subcooled liquid, or superheated vapor, or enthalpy, or temperature, saturation temperature, critical temperature, sublimation, triple point, change of state, change of phase, balance point, dew point, pressure temperature relationship, and pressure drop. For the purpose of the video, and I don't expect you to remember this, but you may need to just go back. Subcooled liquid. A liquid is said to be subcooled if it's any temperature below that of its saturation temperature. So let's just remember, saturation temperature here is the boiling temperature of a given substance. So we said at atmospheric pressure, the saturation temperature for water is 100 degrees Celsius. However, for every 1,000 meters that we climb or go above atmospheric pressure, then the boiling temperature of water will reduce by 3 degrees Celsius. So that's just something to bear in mind. Superheat, a vapor is said to be superheated if it's at any temperature above that of its saturation temperature or boiling temperature. Enthalpy is the summation of all of the energies to bring it to its present state. So heat is a form of energy. And we have two types of heat. We have sensible heat, which is the heat that we can measure using a thermometer. And then we have what is known as latent heat, which is energy that we cannot measure, and that is the heat that's required to convert a substance either from a solid to a liquid or from a liquid to a vapor. And we're talking about here change of state and change of phase. Okay. Temperature then is the thermal energy, if you like, so it's a means of measuring thermal energy. Saturation temperature is the temperature at which a substance will start to change its state, or change its phase, if you like, or change its state. Critical temperature is the highest temperature that a refrigerant will go to and still be condensable by application of pressure. And sublimation is basically where you will go straight from a solid to a vapor without going through liquid state. So the only prime example that I can give you is dry ice, which is the CO2 pellets. So the dry ice in your smoke machines, you put the dry ice pellets into the smoke machine, and effectively what happens is the pellets will sublimate. They will go, when they start to melt, instead of turning into liquid like a water ice cube, they will just go straight to the vapor smoke, if you like, or the vapor phase. Triple point is the temperature at which the refrigerant will exist at all three phases. So in other words, it will exist as a vapor, liquid and a solid. Change of state is when a substance completely changes from one state to another state. So in other words, a liquid to a vapor or vice versa. Change of phase is the process. So in other words, it's the point where the substance will be at a mixed value. So in other words, it will be going through its change. So it will be a combination of liquid and vapor, or it will be a combination of liquid and solid. Balance point, rate of vaporization is equal to the rate of condensation, which is equal to the rate of compression. Pressure temperature relationship then is about as pressure increases, so will temperature. As temperature increases, so will pressure. As pressure decreases, so will temperature. As temperature decreases, so will pressure. And pressure drop then, basically the definition for a pressure drop is that a fluid will undergo a pressure drop the longer it travels along a length of pipe, or when it meets a restriction. So they're kind of the basic terminology or fundamentals that we just need to be aware of. And again, as I say, I don't expect you to get it now while I'm talking, but you can play this back, or you can. One of the things that I find very useful is that if we use the notes, the information will be there in the notes. There's an equipment book that has been supplied as part of your notes, so you'll find that Shane has given you an equipment book there, which is, if I just bring this guy up here, it's this. So I think it's refrigeration equipment book here. It's a PDF. If he hasn't sent it to you, I'll make sure that you do have it. But if I just double click and open it up, you can see this is the thing, and it has all of the contents of this course in terms of what we need to know: vapor compression system, service gauges, service manifold, explains you how to remove gauges, and explains how the different valves work, and so on and so forth, and how to pump down and how to charge systems and so on. Okay, so it's quite a useful book. It's a reference book for you to go back to and to use. So if there's anything that maybe you don't understand because of the way I'm explaining it, then you can refer to this book. Or equally then, if there's anything that you need more clarity on, again, you can refer to the book, or you can just come back and ask me to explain it a little bit better. Okay, forms of heat transfer, this was covered last week, so I don't need to go into it. Pressure temperature relationship, we kind of did that. This is where I was telling you about water boiling at atmospheric pressure. And I told a little lie. I said 3 degrees is actually 3.4 degrees, but I was close. This again is just explaining that, so Brendan would have done that in detail. I don't need to go in it. This is the vapor compression system that I was talking about. Again, I don't need to go into it in too much detail. This is about your superheat zone and condensing zone and so on. And again, we can go back over these notes if we have to, but this is kind of just where we were at last week. Now, what I was trying to do is, if I go back to this original diagram, which is this one here, and I said to you these are the 4 main components, and then we go to the very last diagram where I said everything else is an accessory. This is kind of just showing you a schematic of the types of accessories that we could expect to get. This is the oil separator that I was referring to earlier on. These are pressure safety devices: high side pressure safety device, low side pressure safety device. Again, we have our these are what are called as ball valves. So they're basically just shut off valves. This is a filter dryer to catch any potential moisture and small filings of dirt that may have got into the system for any reason. This is just another ball valve. So again, you can see by adding a ball valve either side of the filter dryer. Now that's not often the case, but the reason for doing that would be to allow us to be able to change this dryer without actually having to pump the refrigerant down into a liquid receiver, or remove the refrigerant by use of a reclaim or recovery system in order to be able to change the dryer. In other words, what we also have to be aware of is that regulation, i.e. the F-gas regulation, makes it illegal for any refrigerant to be deliberately vented off to atmosphere. So we must take every reasonable and commercially viable steps as refrigeration engineers to ensure that the refrigerant stays within the system, or stays within sealed systems, and does not exit the systems and enter into the atmosphere. Because refrigerant either has global warming potential, or it has ozone depletion potential, depending on whether it has chlorine in it. If it has chlorine, it's going to affect the ozone, and if it's a hydrofluorocarbon, it's going to be a greenhouse gas, which is going to affect global warming. Okay, other accessories: solenoid valve used to pump the system down. So in other words, once that solenoid valve is de-energized, refrigerant won't go into the actual evaporator, and if the compressor continues to run, the vapours pulled out of that evaporator back into the compressor, discharged into the condenser, into your liquid line, and as far as the solenoid, it won't go any further. Eventually then the low side of the system runs out of any vapour, and your LP pressure switch is set to make sure your compressor and your system doesn't go below zero, so therefore it will break the electrical feed to the compressor and the compressor cycles off. This is representing your thermostatic expansion valve. So that's your metering device, if you like. And this little bulb here is measuring the temperature of the vapor, the sensible temperature of the vapor as it exits the evaporator, and that has a corresponding pressure. So in other words, the refrigerant inside in that bulb is the same refrigerant that's inside in the entire system, and the pressure then, the related temperature will give it the related pressure, and that will push down on the diaphragm, which will force the valve to open, which allows more liquid going in. But the opposing pressures on that diaphragm will be the evaporating pressure, which remains constant at minus 20 degrees, and the spring pressure. And those two pressures combined are the opposing pressure to the bulb pressure. So if those two pressures are greater, and they're fixed as well because the spring is fixed, the spring pressure is fixed, the evaporating pressure is constant, it stays fixed. So those two, if they're greater than the bulb pressure, then the valve will start to modulate in the closed position. If they are less than the bulb pressure, then the valve will start to modulate in the open position. The cooler the refrigerant is as it exits, the less pressure pushing down, so the valve will start to modulate in the closed position, therefore reducing the amount of refrigerant that goes into the actual evaporator, therefore causing the liquid to boil off sooner inside in the evaporator, therefore giving a larger area over to the superheat zone, therefore increasing the temperature, the sensible temperature of the refrigerant as it leaves the evaporator, thereby increasing the pressure that's in the bulb down on the diaphragm, thereby forcing the valve open, allowing more liquid in. More liquid in means that it boils off later in the evaporator, which reduces the area that you have for superheat zone. And this is what I was saying about the superheat moving between, I said to you it moves between 5 and 8, which is the superheat value, a difference of between 5 and 8. So when you're at 5 degrees, what you'll find is that there is less pressure pushing down on the diaphragm, so the valve starts to modulate in the closed position. And when you're at 8 degrees or anywhere in between, there is more pressure pushing down on the diaphragm, so the valve will start to modulate in the open position, and you will find that your superheat constantly moves between that parameter. And what actually happens is that this, if you can keep the doors closed and you have everything down in temperature, this valve is designed to sit at 6, so to give you a constant superheat of 6 degrees. So it tries to sit in equilibrium. It tries to sit in the middle at all times. It doesn't want to go. It doesn't want to be fully open. It doesn't want to be fully closed. It wants to be at equilibrium. It wants to be in the middle. Okay, so that is kind of just a refresher of what we covered last week. Now, what I want to do for you for this week is, and Shane will email them on to you, there are a number of class exercises that we will have to go through, and Shane's going to email them on to you about it. This is one of them where you actually label all the components, and then there's another one later on in the thing. So Shane's going to send you on the actual Word document. I think he showed it to you last week and was a little bit worried about giving it to you. This is the second one here, whereby you have to compare the two and decide which system is the problem, and then when you decide which system is a problem, you have to say what is the problem. So in actual fact, this one says normal operation, so the one on the left is working normally, the one on the right is basically the customer's called you and said it's not achieving temperature. You have to look at the two pictures and come up with an explanation as to what you think the problem is. But I'll help you with that just a little bit more, and I think there's one more exercise in this slide about setting the pressure switch, and then in the handout that you're actually going to get, there's another exercise which is kind of a fault finding exercise, and it just doesn't show up on the slides there. Okay, so that's that's one piece of information that we need to get. Now, effectively, what we need to be able to do for to meet the learning outcomes is we need to be able to produce a portfolio, and we need to be able to demonstrate that we had conducted those class exercises and learned those class exercises. And then the final thing that we need to do is, or the final two things that we need to do is we do a practical demonstration that we understand how to access the system and take some readings off the system, fit our gauges safely, remove our gauges safely, and so on. And then the other thing is that we need to do a theory test as well. So the portfolio is in here. It should be there. All right. And effectively, what we want you to do is we want you to, by using the simulator, we want you to complete, I think there's actually 12 exercises. So we want you to complete these 12 exercises. And what that means is that, and you hand up those exercises at the end of, so on the last day you will bring those with you. What that means is that you're going to get a pen and paper and you're going to sit down, and for example this one here, it says examine the refrigeration training rig. So what I would suggest you do is that you draw a simple diagram. So the simple diagram can be, if we go back into our refrigerator, it can be that, or it can be it can be something like this, or it can be well, that's a bit complicated, or it can be just as basic as this one here, or if you like, it can be the simple diagram that you draw. If I get rid of this guy, the simple diagram that you draw can be it can be this guy here, for example, if you decide that this is the one you want to draw, or it can be something like this. Okay, so it's kind of up to yourselves in terms of the diagram. The diagram is supposed to help you explain what's going on. So if we go back to the portfolio, and the portfolio is basically saying here that examine the refrigeration training rig. So that's what I would suggest that you would actually, so again, this is if they go into camera, we go into goal. So basically camera, goal, we end up in this view here, which is this rig sitting on the bench, okay, which is similar to the rig that we have. Okay, now if I go, for example, camera, room, I'm in the cold room. Yes.
Yeah. See that you the saying here. See that you told me that we have to draw. We have to pick one draw and 10 of them, like, yeah.
So what we have to do is, yes, can you hear me? What we have to do,
yes,
is we have to go into this viewpoint here in the simulator, and we have to draw what we see here on the simulator. So what you have to do is you have to show in your drawing that this has a condensing unit, a liquid receiver, an evaporator, a compressor, a dryer, sight glass, solenoid, thermostatic expansion valve. And what I suggested was that we would take this drawing here, without the numbers, you don't need the numbers, but you can see there's a compressor, there's a condenser, there's a liquid receiver, there's your dryer, sight glass, expansion device, evaporator. These valves here, this is your suction service valve, your discharge service valve, liquid receiver service valve. But on your drawing, you only have a liquid receiver service valve, and in actual fact, on the suction side, we have a suction service valve, but we also have on the suction pipe a Schrader valve. And again, if we need to understand the difference between the valves, I'll refer you to the equipment book, and the equipment book explains to you about the various different service valves that are there, just to help you understand.
Yeah, that is given the test, like, we have to draw a 1 out of 10, yeah.
Say again?
Any of them. When we go to the test, like, so we have to draw one of the as a 10, just one draw.
Just one drawing?
Any of them.
One drawing?
how many of that, the out of 10?
Yes, it's whatever's easiest for you. You don't have to produce. You don't have
We
to.
have to pick.
You decide what schematic. So I'm just looking for one schematic drawing, and I just gave you examples of how it might look.
Okay.
Okay, so we only need
That's fine.
one drawing. Now, what's important in your drawing is that it reflects the number of accessories and components that you see here in this camera view. So as long as your one drawing shows all of these items, that you can explain it. So what you're being asked to do, if we go again into the portfolio, you're being asked to examine the refrigeration training rig located in camera menu goal. Describe with the aid of a schematic diagram, so this is what we mean, the assembly and operation of the system, and in particular detail the normal conditions of the refrigerant gas as it passes from component to component. So effectively what that is asking you to do is it's asking you to draw a schematic, and as I said to you, the schematic could be a simple drawing as like this, and then it's asking you to say, well, we have high pressure, high temperature, superheated vapor exiting the compressor, entering into the condenser where it desuperheats from a high pressure, high temperature vapor, and then it begins to condense from a high pressure, high temperature vapor to a low pressure or to a high pressure, high temperature liquid, where then it subcools and exits the condenser as a high pressure, high temperature subcooled liquid, enters into the liquid receiver, exits the liquid receiver and enters into your liquid line, passes through a filter dryer sight glass before it enters into the thermostatic expansion valve, where it undergoes a pressure drop and enters into the evaporator as a low pressure, low temperature liquid. You don't need to worry about flash gas for the moment. Travels through the evaporator and eventually boils off in the evaporator, so that at a given point in the evaporator it becomes 100% low pressure, low temperature vapor. It exits that vapor, enters into the compressor and continues on its way. So you just need to be able to draw the diagram and write that down, and that's what the conditions, that's the typical conditions. So in other words, that you understand this here, if you wanted to draw, if you wanted to actually go, and the reason why a lot of these diagrams are say for the metering device, it's in the middle and so on, you can literally split this down, and you can say over here to the right, to the top right hand side is high pressure, high temperature vapor, bottom right hand side high pressure, high temperature subcooled liquid, lower left hand side low pressure, low temperature liquid, top left hand side of my screen low pressure, low temperature superheated vapor. And that would suffice as long as it shows that you understand the different conditions the refrigerant is at as it travels through from the condenser to the evaporator. So from as it's pumped by the compressor to the condenser, from the condenser through the metering device into the evaporator, from the evaporator drawn back to the compressor again. Is that fair enough? Okay, I'll take it to silence. Nobody turned on the mic. Okay, now. So that's the first, that's what you're being asked to do with the first item. The second item, it says the control system on the Gold simulator consists of a power on-off button and a solenoid on-off button. Identify how a control system operates to cycle on and off the compressor during temperature fluctuations of a small butcher's real-world cold room or similar refrigeration system. So, what that means is, because this is a training rig, we don't have a room stat fitted to it. We just have a typical on-off switch to give a power on or power off, and we have a solenoid on-off switch to energize or de-energize the solenoid. If we go into a typical butcher's cold room, which is this one here, this is representing a butcher's cold room. The first thing that you will see is there's a thermostat and pressure switches, but the thermostat, here's the thermostat, it's hanging in the room itself of the butcher's cold room. And it's set for +1 degree. So in other words, what we're trying to do is we're trying to stop refrigeration from continuing once the room temperature reaches plus 1 degree Celsius. So this thermostat is measuring the room temperature, and it's set for 1 degree Celsius. So what you're being asked to do is describe how does that room stat send a signal to the compressor to ask the compressor to stop running. And so effectively that the portfolio is just basically saying instead of this setup that we have here, which is an on-off setup and requires somebody or a human being or whatever to come and actually physically flick the buttons. What it's asking you then is, well, if there is no one to flick the buttons, how does it do it automatically? Excuse me. So really what that means is that this room stat sends a signal to the compressor and tells the compressor to switch off. And the question that you're being asked is, how does it do it? So I'm going to give you the answer, but again, I need you to be able to study it yourselves and write it down. So this is what the portfolio is asking you to do. It's asking you to write it out step by step, the sequence that happens. Now, there are two types of systems in a refrigeration world. There are what's known as on-off cycle, which is literally the compressor is either on or it's off. And then there is what's known as pump down cycle, which effectively is that the compressor will pump the refrigerant down into the liquid receiver before cycling off. So in this case, in the case of the picture that we have in front of us, this is a pump down. This has the control system is wired to create pump down every time the room reaches temperature. Equally, if I just click out of here, because there's a solenoid fitted to our own training rig, this is also a pump down system. So therefore what you have to be able to do is describe the pump down process in order for you to be able to satisfactorily answer that portfolio question. So this question that we've been asked in the portfolio, which is this one here, describing the control system. So the typical answer that you're going to give, if we take this here, or we can take this one, it doesn't really matter, but we take this one here. Effectively what you will notice is, probably it's not easy to see, but there is a kind of a fine dotted red wire which is wired to the coil of the solenoid valve. Okay, now on YouTube, I don't know if Shane has sent you the links, there is a small little video which explains how a solenoid valve operates, and we kind of took it apart. It's one that myself and Shane did, and we kind of took it apart just to show you how it works or whatever. But literally, if I go on to this one here, here's a solenoid valve. That's a solenoid valve here, okay? And we can actually see where the control cable, so in other words, the solenoid valve gets its signal, or its 220 volt supply, to energize the solenoid valve from the room stat. So this is representing your room stat here, and effectively what happens is that when the switch is made on the room stat, we're getting a live feed to your solenoid. So you get your electrical alive feed to your solenoid coil. That energizes the coil, which is basically a magnetic field, which will pull the valve stem out of the body of the solenoid valve, which means then that refrigerant can continue to flow on through the metering device and into the evaporator, and then that refrigerant is drawn by the compressor back and discharged and continues the cycle. Now, as soon as the room temperature is reached, so in our previous one, our stat says plus 1 degrees. As soon as that room temperature is reached, there's a little bellows in here. And it's again, you've got your spring pressure that you have set, so our bellows and the bellows pressure. So those two opposing pressures will decide whether the switch is closed or open. So obviously when we get down to a lower temperature, your set temperature is going to be, so we get down to our minus 20 in this case, or plus 1 in this case here, whichever temperature we're dealing with. Then the way this is set up is that as soon as you reach your room set temperature, then the spring pressure will be greater than the bellows pressure, and therefore the contact is open, breaking the feed, the electrical feed or the live, to the actual solenoid valve. So in other words, the solenoid valve comes to is referred to as what we would, or it becomes de-energized. So we refer to it as being de-energized. As soon as that coil is de-energized, there's a little spring on the top of the valve stem which will force the valve, the spring is actually going to force the valve to go back down into the body, or the stem should I say, back down into the body of the valve. Okay? And once the stem is in the body of the valve, it basically then will prevent any refrigerant in this liquid line to go past the solenoid. So in other words, it doesn't allow any of the liquid to go through. Now, this is the solenoid valve here, this is the solenoid valve here. Forget for the moment, in actual fact, a better way of describing it is that once my solenoid is de-energized, liquid can't go into the evaporator. The resultant refrigerant that's in, or the remaining refrigerant that's in the evaporator is drawn out of the evaporator by the compressor, so that at a given point inside in this evaporator, it runs out of refrigerant because no new refrigerant is coming in to replace the refrigerant that's been pulled by the compressor out. Therefore, the back pressure, in other words, the pressure going back to the compressor, goes down or starts to drop, it starts to decrease. And basically when it gets to zero, we have what's known as a low side pressure switch. So it's the pressure switch that makes or breaks the electrical feed to the compressor. So in other words, again, there's a bellows and a spring pressure. So we would set this at maybe cut in a 2 bar, differential at 2 bar. That means that when the back pressure gets to 0 bar, the actual contact, the electrical contact will open. And that once that opens, that kills the power to the actual compressor and the compressor stops running. As soon as 2 bar pressure comes into the back pressure onto the bellows, that 2 bar pressure then will force the contact to close because it will be higher than the spring pressure. Therefore, once the contact closes, electrical feed returns to the compressor and the compressor starts. Best way of maybe trying to show how that works is you can go and practice. We go into our tools, and what we have is we have the purge, we have the recovery, we have pump down, we've recharge. So it's pump down that I want to discuss. But you see there it says you must purge and attach the gauges first. So the first thing, and I'm sorry if I'm kind of jumping ahead, but I'll jump ahead and then I'll jump back again. So the first thing that we all must learn before we ever put gauges on the system is we all must learn this purge sequence. Okay? Now what purge means effectively is, it means that we as human beings, when we go and access a refrigeration system, we must take every precaution not to allow air, atmospheric air, or any kind of air, enter into the system. The reason why we don't want air into the system is because air is an enemy of your refrigeration plant. The main problem with air is that it contains what's known as moisture, and moisture, when it mixes with a refrigerant oil, causes that oil to become acidic. Moisture, if it gets into the system, freezes at 0 degrees Celsius, so potentially when it gets to the expansion device and the expansion device creates a pressure drop, that could be lower than 0 degrees Celsius, so you have potentially a freezing of the moisture or freezing of the water content, causing an ice blockage, preventing the refrigerant from going past the metering device. And then air is a non-condensable, so therefore when air gets into the condenser, it won't condense back into a liquid. So therefore what happens then is you get the same symptoms as a system that has excess amount of refrigerant, a system that's overcharged with refrigerant, and you won't achieve cooling because you're upsetting the balance point. So we do not want air to get into the system. Atmospheric pressure, you've seen from an earlier slide, and probably Brendan covered it in detail last week, is 1 bar, okay? Therefore, we see our gauges here. If we look at our gauge here, our gauge is registering, and this one hasn't been sorted out, so just ignore this one for the moment. I'll get on to Shane about that again. But there's our gauge is registering at 0 here, 0 bar, right? So in other words, gauge pressure is going to be 1 bar less than atmospheric pressure. So in other words, this gauge pressure is reading 0 bar, but the hoses are exposed to the air. So in other words, these hoses have air in them, because there's nothing to stop air entering into these hoses. So when we go and put a set of gauges onto the system, as a precaution, and this is what we would refer to as inadvertent venting as opposed to deliberate venting. As a precaution, we have to vent some of the vapor that's in those lines out to atmosphere. But in theory, what we're actually doing is we're only venting the air that's in the lines. Because in theory, when I go and connect this blue hose, so in other words, there's positive pressure inside in this system. There's a Schrader, so this is a Schrader connection. It doesn't matter if I do it via Schrader or if I do it via the suction valve, service valve, but I'm just going to do the Schrader. A Schrader operates in exactly the same way as the Schrader on your car tire. So when I'm putting air into my car tire, there's a little Schrader inside it, and effectively there's a depressor in my air hose. Well, there's a depressor in these lines here. So as soon as I put that on to this system here, I'm depressing the Schrader core valve, and whatever pressure's in my suction pipe is now entering straight into my gauge. It's reading my gauge manifold here, right? So I'm getting a pressure here of 4.5 bar. Now, the air that's in this line is actually lighter than the refrigerant that's entering into this line. So the air is being pushed along the line and pushed up as far as the gauge, okay? So the air is sitting on top of the refrigerant. So the purging mechanism that I'm going through, in theory, will push the air out, and the idea is that from practice we will know that you don't purge for too long, and you purge long enough just to push the air out, and you kind of take an educated guess as to how long you need to purge for and when it stops being air and starts to become refrigerant. And we're talking about very small volume of air here, so you don't really need to purge for all that long. So one of the videos that we put up was about purging, and some of the feedback and some of the questions that we got was, oh, well, we usually leave that, we give it a good old purge. It's not really necessary to prolong the purge. You're just giving it a short, sharp purge to remove the small amount of air that's in the lines. The air that's in the lines isn't all that great. So once we have attached this blue hose to the Schrader fitting, the positive pressure is pushing the air along the hose to the top end of the hose. Now, in practice, you will see some guys, and they will actually go and loosen this part here that's connected to the manifold and let the air go out, and then they'll do the same on the liquid side. They'll fit it to the liquid side and they'll loosen it at the red point here. Problem is that as soon as you put it on the liquid side, you're releasing liquid off. Problem with releasing liquid off is that you'll burn your hands, and it's not really recommended as part of the regulation. So you should, at all accounts, avoid releasing liquid off into the atmosphere, for health and safety, and also because you're venting refrigerant. So you're venting the liquid refrigerant off. So there's a better way of doing it, and that's this purge mechanism that I'm explaining to you. So you'll notice that as soon as I connected this blue gauge, the blue gauge here, the writing changed. So now it says stage 2A. So we had stage 1, which would fit the blue. Now we have stage 2, which is attached the gauge to the high side service valve. So this is our red line representing our high side, and we go over here. Now, when you come to the real world, what you will find is that there is a little black cap fitted to this service valve, and I suppose the best way of describing this service valve is if I go into this here, to this book here, and we go into valves and gauges, and we go down along here. This kind of gives you a picture. This is a picture of the service valve that we're dealing with. So this is the cap that I'm referring to, and that cap is just a kind of a seal. So you can see it's a valve seal cap, whereas B is the valve stem. So what we're doing is, before we do anything, we will take off the seal cap, the valve seal cap, which is a little black cap. We'll take that off, and then we will use what's known as a valve ratchet. And we will make sure that the valve stem itself is in the back-seated position. So this refers to the back-seated position. So in other words, what we're trying to do is we're trying to make sure that this valve stem is anti-clockwise. It's in the back-seated position. And what you'll notice this is cutaway is that when it's in the back seat position, this black here is representative of refrigerant. So all this area here is refrigerant. But you can see there is no refrigerant going to the service port when you have your valve in your back-seated position. So that basically means that once I go and I fit my red gauge here, after I've taken off the cap, and I fit my red gauge, when we go around here, you will see there's no pressure registering here on my gauge manifold, and that's because I have this valve in the fully back-seated position. In other words, the refrigerant is only coming from my receiver and entering into my liquid line, and it is not exposed to my service port. Okay? So that's why I'm not getting anything here. So in order to be able to get a pressure reading on this gauge line here, I actually need to crack my service valve, right? So in other words, this is called midway here. So I need to actually just crack it. In other words, by just giving it 1 or 2 turns towards the front seat position or the clockwise position, I move this stop valve or this plunger away from the body, and therefore refrigerant, now you can see where the black is entering in behind the actual valve stem and has now access to the service port. So we do not want this to be in the crack position or the midway position when there's no cap. So F is the seal cap. So when there's no cap on my service port, we do not want this valve stem to be in the cracked or midway position, or even the front seat position, which is all the way forward. I think there is further on, but I won't go into it now. Is it up here? Yeah, there it is. There's the fully front seat position. Because if it's in the fully front position, you can still see the black is exposed to the service port. So we don't want to remove this cap while this valve is in a front seated position. So we must always satisfy ourselves that this valve stem here is in the fully back seated position before we ever remove this cap here. So as I say, in this one here, in this position that we haven't cracked the valve. We've left the valve in the back seated position. Now, what we're being asked to do is, we're being asked to take the air that's sitting at the top of this gauge here, right? It's being pushed along the blue hose and it's sitting inside at the top of the gauge. We're being asked to allow that gas, to release that gas from the gauge into the valve body, the manifold body. So the gauge manifold, this is a gauge manifold, it's the manifold body. So how we do that, stage 3 is open the low side manifold valve. So when I open this valve here, refrigerant is now going from my gauge into the manifold, into the body itself, so into this black area here. Now that means that this yellow line, and this is something that you're going to have to be careful of as well, when you come to site, make sure that yellow line is blanked. We do not want that yellow line to be exposed, because as soon as I open this valve here and allowed refrigerant to go from my blue gauge into my valve body, or into my manifold body, my gauge manifold body, or into the manifold, I suppose is the better way, I'm then allowing refrigerant to enter into this yellow hose here, which would be allowing it to go off the atmosphere if this yellow hose wasn't sealed off as it is here. Okay. So now there's refrigerant in the manifold, and it says open the high side manifold. So we go and we open the high side manifold, and suddenly you will see the refrigerant that was in this gauge line here has now gone into the manifold, and then it goes from the manifold into this gauge here, right? And subsequently it goes from this gauge here into the red hose line. So now we've got the air pushed all as far as this point here. So there's refrigerant, as you can see, there's about 4.5 bar of refrigerant, and the air stays on top of the refrigerant because it's lighter than the refrigerant, and it's sitting here at this point here, okay? And it says slightly loosen the high side gauge hose at the service valve. Oops. I don't know what happened there. Okay, it can be a bit finicky, but we'll get there. Okay, so now we just have to go up here, see if we can do it. Okay, so when I slightly loosened it, I don't know why, normally it makes a kind of a purging noise. So again, I'll just check with Shane. But when I clicked on that button, what I wanted to hear was the noise. So you would have heard the gas just escaping. And then it says close the low side manifold valve, which is stage 6. So I just want to... just bear with me, because I just want to see. It might be that I don't have sound on. So hold on now, let me just see where my sound is. So I do have sound, that's okay. I just want to check. So I'm just going to go through the steps. And while I'm going through the steps, you can watch this happening down here. Okay, so it's not making the noise. So it used to make the noise. And basically when I did this last step here, stage 5, when I did stage 5, what I was expecting to hear was the gas to come out, and basically what it's only a short, sharp blast, so it's not refrigerant gas per se, it's actually the air that's sitting on top of the hose that's been released so that you don't add it to the system, okay? Then when we have that done, we then close our manifold, because if we don't close this manifold, then basically we have high and low side exposed to each other through the manifold. So we have to close the low side manifold, and equally we close the high side manifold, okay? And now that we have the two manifolds closed, or the two valves on the manifold, the high side valve on the manifold and the low side valve on the manifold closed, the refrigerant that's in the high side of the system is only exposed to the high side gauge, and the refrigerant that's in the low side of the system is only exposed to the low side gauge. It says the purge is complete, so now I close, okay? And basically then what happens here then is I have to go to my tools, I get out my valve, I fit it to my service valve, I crack it, so you can just see I'm just doing a turn there, and by cracking it then I'm getting the actual high side pressure, which in this case is 15 bar. So we can see that on this system we have 15 bar on the high side of the system, and we 4.5 bar on the low side of the system. Now, to get back to the point that I was trying to make to you, which was about pumping down the system, or the system being controlled as a pump down. So just to remind us, what we were asked to do is we were asked in this point here is to describe the control system for a typical butcher's cold room. And what I'm trying to do is use the simulator to demonstrate to you how a typical butcher's cold room works. So what I did was I went and I used this diagram here, not that diagram, sorry. This diagram here, which is a typical butcher's cold room. And I explained to you that once the room stat has reached +1 degrees, the normally closed contact opens. That kills the electrical feed to the solenoid coil, which becomes de-energized. That means that the valve stem, which has a spring on the top of it, is now forced to sit back down into the valve body of the solenoid valve. That prevents any further liquid refrigerant from entering into the evaporators because it's effectively closed. The compressor pulls all of the refrigerant out of, or the remaining refrigerant that was in this evaporator, out of the evaporator via the suction pipe all the way back, and discharges it back into the high side of the system and back into the liquid line and on into the up as far as the solenoid again. But because the solenoid is closed, no more refrigerant can enter into the evaporator. So what happens here is the evaporator eventually runs out of refrigerant, and when there's no more refrigerant in the evaporator, the pressure on the low side of the compressor drops down to 0, and the pressure switch, which you can see fitted here. So basically what you will find is that there's a pressure switch, and what I'm trying to study here is which one is connected. So basically there's a low side pressure switch and a high side pressure switch, and I'm trying to figure out which one is connected to the low side, and so it's the one that has the pipe to the suction side of the system. The low side is the low side. It's quite hard to see here. Quite hard. There's the suction pipe. There's the pipe work. So this is representing your low side pressure switch, and that basically is set up to the electrical. So in other words, the control of this is that it supplies the electrical power, the 220 volt, 380 volt, whatever it is, 220 volt in this case, to the compressor. So once the refrigerant empties out of the evaporator and the back pressure drops to 0, this pressure switch contact will open, thereby killing the power of the compressor, and the compressor cycles off. Okay. Soon as so there's a built-in differential inside here. It could be anywhere between 2 and 4 degrees, normally in high temperature, so that you don't have short cycling of the compressor. You would have maybe a 4 degree differential. It could be even as high as 6 degrees, but normally it's about 4 degrees differential. So when this rises up by 4 degrees, so in other words, when the room temperature gets to 5 degrees in temperature, what you will find happening then is that the solenoid will then the contact will close on the solenoid, which will send electrical power to the solenoid valve, and then the solenoid valve then is energized, which will pull the valve stem out of the body of the valve, which will then allow liquid to enter into the evaporator. And when liquid starts to enter into the evaporator and through the metering device and so on, there is a back pressure coming back on the compressor, so the pressure starts to rise at the compressor, and this is picked up by the low pressure switch. So the low pressure switch then, as soon as the predetermined pressure, and normally it's about 2 bar, as soon as the 2 bar back pressure reached, that closes the contact on the low pressure switch, which then sends electrical power to the compressor, and the compressor starts up and starts to run and continues to run until pump down sequence starts again. So what I was trying to do is trying to show you that. So what we can do here is we can go in here, not info, sorry, we can go into tools and we can show pump down. So effectively it says backseat your high side service valve. So again, the pump down in this case is just showing you how to take off the gauges, right? But in order for me to be able to backseat the valve, or in order for me to be able to demonstrate pump down on this system, I need to make sure that the valve itself, or that there's no liquid going to the high side. So sorry, this is giving me a bit of jip. Okay, so in other words, what I'm doing is I'm just stopping any liquid refrigerant from going into the gauge manifold. But effectively, what I'm trying to show you here is how the solenoid pumps down when it's de-energized. So I'm just going to get all the liquid that's in my, and this is basically showing you how to take gauges off as well without losing them to atmosphere. I'm basically taking all the liquid that's in my red line. So in other words, because I've backseated here, I've now gone to the stage where I've returned the valve to this position here. So there will be a certain amount, so this is backseated, but there will be a certain amount of refrigerant that's in this line, that was in this line previously. So that refrigerant that was in that line there, now that I've backseated, no fresh refrigerant is coming into this area here, but the excess refrigerant that was there it still remains. So I need to just get that out of there first of all. So this is why I allow it to go into the manifold. Then I allow it to go from the manifold across into the low side of the system. And because my compressor is running, the liquid that's there, it boils off before it gets back to the compressor. And now you can see where my pressures have equalized. So I'm now down at about 3 bar and 3 bar, or it's probably 4.5 bar, but the pressures are equalized. Now, what I'm trying to demonstrate is, again, if we just recall, not this one, but when we recall, when I went to this diagram here, what I was trying to is demonstrate that once this solenoid is de-energized, and it has been de-energized by the signal being broke to it, created, so in other words, the room stat breaks the feed to the solenoid coil. In our case, we just switch it off. So we've now broken the feed to the solenoid coil. And by breaking the feed to the solenoid coil, what actually has now happened is, if we look at our own system, this coil here is de-energized. So in other words, my room stat has killed the power to the solenoid valve. No liquid refrigerant can go past this solenoid valve. And what you saw happening then on my gauges is I went from 4 bar down to 0, right? 0 is here. There's a little programming problem. It shouldn't be registering -1. It should be actually just registering 0. If it goes into -1, you're actually bringing it into a vacuum. And that's no good, because you will draw air into the system, because bringing it into a vacuum means that you're in a negative pressure, and we've got 1 bar positive pressure.
Excuse me.
Yeah. Yes.
Yeah. See that some cold room don't have the solenoid valve. However.
Yes.
And they'll leave the high pressure and the compressor, and compressor work with the through the the thermostat.
Yes. So that, as I said at the beginning, was on-off cycle, and I was saying there are 2 types. There's the on-off cycle, which is what you've just described. And there's this type, which is the pump down cycle. And because you're being asked to describe the control system that we see in front of us, then I'm asking you to describe the pump down cycle. But you are correct. There are 2 different ways. So yes, the room stat will either make or break feed to the compressor, and that's the on-off cycle. Or the room stat will make or break the feed to the solenoid, and that's the pump down cycle.
Alright, so if there's no solenoid valve, and compressor can be stopped through the thermostat, and leave the the high pressure and the low pressure same way, and then there's a thermostat kick again to the through the sorry, it's a compressor start through the the thermostat again.
Yeah, so effectively what you might find in a lot of scenarios is that the LP switch doesn't exist, maybe, and on other occasions you might find where is an LP switch that it only really comes into effect as a safety device. So it's only when the refrigerant runs out or escapes from the system because of a human error, then it will cut the compressor to prevent the compressor going into a vacuum and causing further damage. So all you will find in your system is that the stat energizes and de-energizes the compressor. So during normal operation, compressor will stop via the thermostat, and the pressure switch only comes into effect when there is no gas in the system and acting as a safety device.
All right, that's fine.
Okay.
Thank you.
So that is the portfolio number 2, is the it's just explaining to you or trying to get to you to explain the control system for a system that has a solenoid valve, in other words the pump down control system. So it was asked you here on the portfolio the control system here, how does it work, how does the operate the cycle on off on the compressor during temperature fluctuation of a small butcher's cold room or similar refrigeration system. Now if you're more comfortable describing a system that cycles on and off without a solenoid, that's okay too. So either or, whichever way you're more comfortable with. If you decide that that's what you're used to working with and you want to describe the on-off cycle, I'm okay with that as well. But we'll look at it together. So basically when you produce it, we'll have a look at it, and we'll have time when we're here on the day to work at it.
Okay, thanks.
Okay.
No, the solenoid valve will be better. Solenoid valve is better job anyway.
Yeah.
Yeah, because it's there, saves the compressor, and work through the the high pressure switch or low pressure switch.
Exactly. Yeah. Now, what tends to happen with the high pressure switch is that the high pressure switch tends to be again just a safety. So we have this is our pressure switch here, and we can see that the capillary for the high pressure is there on the high side of the system. So it doesn't really matter whether you have it on. It's high pressure regardless of whether it's on the liquid service valve or if this compressor had a discharge service valve, it could be there. It can be on the discharge line, so anywhere on the high side of the system. And it really only comes into effect that if the pressure builds up to unsafe pressure, so it's going to exceed the maximum working pressure of the system. Whereas the low side, again, it's there. You can see where the capillary is here on the suction side, so it's getting a capillary or low side reading. And again, the low side pressure switch is there for two reasons. One, for safety, or the second one is to cycle on off the compressor when there's a solenoid fitted and you're trying to use a pump down. Now, using a pump down is actually better because it's less harsh on the compressor when it starts up, because the compressor starts up on a low pressure as opposed to it having to start up on a kind of full of gas. When the compressor is full of gas and it starts up on, say it's sitting there at 10 bar pressure and it has to start, then that kind of creates extra pull on the compressor because there's a higher torque to get it to start. Whereas when you're starting it from a low pressure, from a 2 bar, 1.5, 2 bar pressure, there's less of a drag or less of a overload on the actual compressor, less chance of the compressor going out on overload.
All right.
Okay, now getting back just to look at this other one, it says there are no labels on the Gold simulator. Confirm the refrigerant type circulating in this system and describe what methodology you would use to determine the same. Again, without going through it all, but you can see how it's how we can go through it, and I'm conscious that we're kind of getting close to quitting time as well. So what I'm saying here, and I'm just going to speed it up just a little bit because I want to make sure that we all have an understanding of all of these. Sorry, I forgot what I was saying. Oh yeah, there's no labels on it, right? So what that's asking you to do is it's asking you to use your slide rule, and by using your slide rule, you have to determine the pressure temperature relationship. So basically how this slide rule works, you've got your different types of refrigerant down along here. You've got your pressure in absolute or your gauge pressure. So in our case, we're reading gauge pressure, okay? So if we look at the high side, for example, looking at my gauge pressure going across along here, I have 15 bar. Where did I get the 15 bar from? I got the 15 bar when I fitted my gauges. Unfortunately, I've taken my gauges off, but let's fit the gauges again. So let's just do the purge again. So I'm going to do it quickly. You guys can practice away when you're on your own time. I'm just going to fit on the gauges. I'm just going to do my purge, and then I'm going to okay, so where did I get the 15 bar? There it is there. If we look at 15 bar. Now, the other thing just to make you aware of is your gauge manifold is also a slide rule. So if you look inside, look on the outside first. The black one is all pressure. This is where I'm getting my 15 bar. But if we look at the inside, we've got 407C, we've got R22, we've got 134A, and we've got 404A. And then you can see here degrees Celsius. You can see it over here, degrees Celsius. It's the same there, degrees Celsius. So in other words, these figures here represent the temperature, the corresponding temperature for each one of these refrigerants. So every refrigerant has its own pressure temperature relationship. So that's why when I went to my slide rule, this slide rule that I have is exactly the same slide rule as the gauge manifold that we're looking at. So when I go to 15 bar, which is here, I'm going to gauge pressure, and remember we were saying that the gauge pressure is 1 bar less than absolute pressure. So this one is absolute, and you can see that's 16 bar, whereas the gauge pressure is 15 bar. So we're only going to worry about gauge pressure. And then for each one of these refrigerants is a corresponding temperature. So for 134A, that's the corresponding temperature. For 404A, that's the corresponding temperature. For 507, that's the corresponding temperature. For 407, that's the corresponding temperature, and so on and so forth. Okay? So I can either use my slide rule or I can use my manifold to answer the portfolio. So the portfolio has asked us this question here. There are no labels in the simulator. Confirm the refrigerant type circulating in this system and describe the methodology you use to determine the same. So how we determine the same is we apply what's known as the rule of pressure temperature relationship. So if I'm getting the 15 bar here, the corresponding temperature will relate to one of these refrigerants. So in other words, what this gauge is doing is it's actually giving me condensing pressure or head pressure. So my condenser, the pressure inside or the temperature of the refrigerant inside my condenser will correspond with the pressure that's there. So how do I do that? Well, what I do is I get my thermometer and I measure the temperature inside in the middle of my condenser. So remember I said to you, we have desuperheating zone, we have condensing zone, and we have subcooling zone, which is down the bottom here, okay? So we can see down the bottom we're getting a temperature of 28.9 degrees. So that's the temperature of the refrigerant as it leaves the bottom of the liquid refrigerant as it leaves the bottom of the condenser, and that's going to be slightly colder than the temperature in the middle of the condenser. So for some reason, and I'm going to have to hopefully when he's editing this video tomorrow he will be able to realize that he has programmed it out. For some reason this is not allowing me to measure the middle of the condenser. It used to. So I'm going to have to kill Shane. That's why he wasn't here tonight. He must have known when he did this new build that it wasn't working properly. Right. Just to do that, I'm just going to go here, Just again, it's the same thing. I'm just finding a condenser just to show you. I'm hoping this condenser will allow me. Okay, so I've just put the thermometer here in the middle of the condenser. So remember I said there was desuperheating zone, condensing zone, subcooling zone. So if you notice when I put it in the middle of the condenser, I'm getting 35 degrees in the middle of the condenser. When I put it down to the bottom of the condenser, I'm getting 28 or 29 degrees, okay? So that the difference between my 35, which is condensing temperature, and the 29, which is the liquid outlet temperature, the difference between the two is my subcooling value. So my subcooling value in this case is 29 minus 35, which is going to be 6 degrees, okay? So my subcooling value is 6 degrees. Now, going back to what we were trying to do, which was this part here, which is just basically saying how would we know what refrigerant is in the system? We know that by carrying out a pressure temperature relationship, pressure temperature exercise. So we said our gauge was registering 15 bar. So again, if I just go back here to the goal, and we said our gauge here was registering 15 bar, and we're saying where we put our thermometer says that the condensing temperature, so the temperature of the refrigerant, or the boiling temperature, or the saturation temperature of the refrigerant, or the condensing temperature of the refrigerant is 35 degrees Celsius. Now I'm deliberately saying saturation temperature, boiling temperature, and condensing temperature, because those three words are used to describe the temperature at which the refrigerant will change from a vapor to a liquid inside in your condenser. Okay? So the condensing temperature is the temperature at which the liquid refrigerant or the vapor refrigerant will start to change from a vapor to a liquid. The saturation temperature is the saturation temperature inside in the condenser. So in other words, the condensing temperature refers to the saturation temperature inside in the condenser. Now what we're trying to do here is we're trying to figure out what refrigerant is in that system. There are two ways of doing it. One is the pressure temperature relationship. The other is looking to see what thermostatic expansion valve is fitted. And the thermostatic expansion valve that's fitted must relate to the pressure temperature of the, must be equal to the pressure temperature relationship of the refrigerant that's circulating around. The problem with relying on an expansion valve nowadays is because there's so many retrofit gases on the market to replace the old refrigerants that are being slowly phased out. So 22, for example, was phased out in 2010. 404A will be phased out by 2020. And so on, but there are drop-in gases coming in all the time, so therefore you might find that there's a 22 valve sitting on your system, but the gas that's in it is 407C or something, or something equivalent, 407C being a drop-in or some kind of drop-in gas. So it's not as reliable as it used to be. So the most reliable way of determining what refrigerant is in your system, if it isn't labelled, now you shouldn't come across a system in today's market that isn't labelled, because under F-gas regulations all systems must have a label on them, and that label must say the type of refrigerant, the weight of refrigerant, the CO2 equivalency, in other words the global warming equivalency that it has in terms of CO2 benchmark, and the words contains hydrofluorocarbon gases as per Kyoto or as covered by Kyoto Protocol. And every system out there must have that label with that minimum amount of information in it. But anyway, getting back to this exercise, we then systematically go through these refrigerants and we see which one of these refrigerants, when if I slide down along here, gives me 35 degrees. So if we look at the green one, which is the first one, 407C, again these go up I think in 2, 4, 6, 8, 40, 32, 34, 36 degrees. 407C plus 36 degrees, so it's not 35, so 2, 4, 6, 8, 40, right? It's 36 degrees. It's close, but it's not close enough. Next one we see, the next one we come across is this one here, R22, and you can see that that's 42 degrees. 2, 4, 6, 8, 50, 42 degrees. Next one we come across is R134A, and we can see that that is 52, 4, 6, 8, 58 degrees. And the last one we come across is 404A, and we can see that that's 32, 34, 36, 38. So it's actually 35 degrees, 34, 35 degrees. So now you're saying to yourself, well, how do we know that it's 36 degrees or 35 degrees? So this is where we are saying, right, okay, it says 34 on our gauges. So this is where we kind of say, okay, it's not giving me, so it's either, it's down to, according to this gauge, is either 407C because we're at 36 degrees, or it is 404A because that's at 34 degrees on my gauge manifold. But hey, we will use the app or we'll use this slide rule, whichever, because slide rules have been replaced with apps, and we will basically see, well, okay, let's look at 134A, for example. We think it might, no, sorry, 407C. Let's look at 407C, which is this one here. So let's go to 15 bar. Let's slide down for 407C. Now, you've got dew and bubble point. So dew point, you can see here, number 2 is the dew point inside the evaporator, and number 1 is the bubble point inside the condenser. So basically we have to say to ourselves, okay, we were looking at the condenser, so we have to look at number 1, and you can see that, look at number 1, 407C, it's actually, now what I mean by dew and bubble point is that because this refrigerant is a zeotropic blend, it is a mixture of a number of component refrigerants. It's a man-made refrigerant, and effectively there is what's known, it has what's known as a slide or a glide, if you like. Basically there is a lag in each component reaching its saturation temperature, and the lag is significant in terms of it's greater than 0.5 of a degree, it's 1 or 2 degrees. Therefore, at a given stage, which is at the dew point temperature or the bubble point temperature, depending on whether it's in the evaporator or the condenser, all of the components reach the 100% saturation, and that is the true evaporating temperature or the true condensing temperature. So in our case, we're looking at our bubble point temperature, which is number 2 actually, because it's inside in the condenser, which is the highest pressure, and this is the pressure enthalpy chart, and the lowest pressure is the evaporator. So because we're looking at 15 bar, we are looking at our bubble point temperature, which is number 2. So if we look at our bubble point temperature, which is number 2, we can see here that we have, there is 31, 32, 33, 34, 35, 36, 37 degrees. The actual true condensing temperature at 15 bar for 407C is 37 degrees. Whereas the actual true condensing temperature for 404A, so there's 31, 32, 33, 34, 35. The actual true condensing temperature for 404A is 35 degrees Celsius. So if we can remember, we went with our thermometer and we went to the middle of the condenser and we stuck our probe here in the middle of the condenser, and when we, that's the top of the condenser, this is the middle of the condenser. When we got to the middle of the condenser, we were reading a condensing temperature of 35 degrees Celsius. We then looked at our condensing unit, or sorry, our gauge, and we discovered that on our high side gauge we have a 15 bar condensing pressure of 15 bar, corresponding condensing temperature of 35 degrees Celsius. So our condensing zone, we put a thermometer in the middle of our condenser measuring the temperature at our condensing zone. Our condensing zone temperature or our condensing temperature is registering 35 degrees Celsius. Our high side gauge reading is 15 bar. Our slide rule shows us that if we have we narrowed it using our gauge manifold, we narrowed it down to 2 refrigerants. So using our gauge manifold, by looking at our gauge manifold, we said to ourselves, looking at the gauge manifold, we said we narrowed it down to 2 refrigerants, and we said that it was either possibly 407C, because that was giving us 36 degrees here, it was giving us 407C was giving us 32.46 degrees, or 404A because that was giving us 34 degrees. So we were 1 degree either side of the actual true condensing temperature, which is 35 degrees. So in that case we said, well, we must go and get a more accurate, so instead of relying on our gauge manifold, we'll get a more accurate reading. So we used our slide rule to get a more accurate reading, and we looked at 15 bar gauge pressure. So again, we brought the slide rule here, there's our gauge pressure here, brought the slide rule to 15 bar, and then we went down along until we came to the 404A, and we discovered, because that's the first one we see, we discovered that that's 35. So the pressure temperature relationship for 404A at so 15 bar is equal to 35 degrees Celsius. That's the pressure temperature relationship for 404A at 15 bar or at 35 degrees Celsius, whichever way you want. 35 degrees Celsius 404A equals 15 bar pressure. 15 bar pressure 404A equals 35 degrees Celsius. Whereas when we went down to the 407C, we could eliminate that, because again, 407C has what's known as a slide. There's a difference between the saturation temperatures of all of the components, referred to as either bubble point or dew point. We took the bubble point temperatures, which is the temperature inside in our condenser, and we discovered that that was actually the bubble point temperature, which was number 2, which is what we decided here. Bubble point temperature was 35, 36, 37 degrees is the true the true condensing temperature, or the true pressure temperature relationship for 407C at 15 bar. So at 15 bar, 407C has a condensing temperature of 37 degrees Celsius, or at 37 degrees Celsius, the equivalent pressure for 407C is 15 bar. So we could eliminate that because we measure 35 degrees in our condensing zone. We know the condensing temperature in our zone is 35 degrees. Therefore, the corresponding pressure for that is 15 bar. That's what we're getting on our gauge. That's what we're getting on our thermometer. 35, 15, it's 404A. We can say that with confidence. Moving on then, using the tools.
Hello, just a quick question.
Yeah. Yes. Yes.
What if you have a high head pressure?
Yes.
Hello?
Yes.
Can you hear me?
Yes. What if you have a high head pressure? That was your question. Regardless of whether you have a high or a low head pressure, pressure temperature is always related. So to help answer your question, I hope you're still there. Are you still there? You still there? Was it Damien?
Oh, yeah.
Yeah, you're there. Okay, Damien. Right. Okay. If you had a high head pressure, you would have a higher temperature. So if I go with the slide rule again, with this slide rule here, and we go with group 2, if I had a high head pressure and I went from 15 bar up to 20 bar, then the condensing temperature that I would get would increase. So if my head pressure goes up to 25 bar, would be the maximum working pressure for a 404A system. So if my condensing temperature for whatever reason got to 25 bar, then my head pressure for 404A would be up here at 55 degrees Celsius, 56 degrees Celsius. It should be 21, 2, 3, 4, 5, yeah. So it's about 55 degrees Celsius, 56 degrees Celsius, yeah. That's the maximum temperature that my condenser can get to, which is the maximum head pressure of 25 bar. So the higher my head pressure, the higher my temperature. The lower my head pressure, the lower my temperature. So that's a very important question that you asked, because one of the things that we will be doing before we're finished is we will be doing some troubleshooting. So one of the things that you will be asked to do, if my mouse comes back to me, one of the things you'll be asked to do is you'll be asked to go into this test skills area, right? And you will be asked to go through these faults. So that's that's the last thing that you do. But this is a chart that we have here that we give you. And this chart here, as the first question it asks you is your back pressure, and the next question is your head pressure. So is your head pressure too low? So really what that question is asking you is that for the ambient conditions that your heat exchanger is exposed to, is that a normal head pressure? So is 15 bar normal? Is it higher than normal, or is it lower than normal? All right, and that kind of is that's why I'm saying to you that this is it's a very, what you've asked there is a very important question, because when we go back here and we seen that we had 15 bar on our gauge, right? When we were registering 15 bar here and it was given us 35 degrees Celsius, how do we know that that's normal head pressure? All right, and how we know that that's normal head pressure is it's based on the air temperature that's coming onto the condenser. So this temperature here, the air temperature coming onto the condenser is 20 degrees Celsius. And the rule is that my condensing temperature should be anywhere between 10 to 20 degrees higher. So all air-cooled condensers, not water-cooled now, just air-cooled. All air-cooled condensers are designed to operate between 10 to 20 degrees higher than so in other words, the condensing temperature will be 10 to 20 degrees higher than the air temperature coming on. So if my air temperature increases to 25 degrees, my condensing temperature will increase accordingly. If my air temperature decreases to 15 degrees, my condensing pressure stroke temperature will decrease accordingly. So in our case here, if I add 15 onto my 20, I get 35 degrees. So it's always midway. So it can go as low as, in other words, with an air temperature of 20 degrees, my condensing temperature can go as low as 30 and as high as 40. So as long as my condensing temperature remains between 30 and 40 degrees, and in our case it's 35 degrees, which is midway, it's halfway through, which is spot on. So we're quite happy with a 15 degrees delta T total. That's what we talk about. So if my head pressure was up at if my air temperature went from 20 degrees to 30 degrees and I add 15 on to 30 degrees, I'm getting 45 degree condensing temperature. So again, that's normal because of the increase in air temperature coming on to the condenser. So remember, in order for heat exchange to take place, there must be a temperature difference. And the higher the air coming onto my condenser, the higher the condensing pressure stroke temperature is going to be. The lower the air coming onto the condenser, the lower the temperature stroke pressure is going to be. So on a summer's day, you might find that goes as far as 25 degrees. That temperature goes as far as 25 degrees. If you add 15 to 25, which is what we have a delta T total of 15. We can have it anywhere between 10 and 20 of a difference. But at the moment, we have a delta T total of 15. So if you add that on to 25, you're going to get, so 5 and 5 is 10. What did we say? 1 and 2 is 3 and 1 is 4. So you're getting 40 degrees condensing temperature. Isn't that correct? Adding 15 onto that. Now, if we're dealing with the fluctuation, it can go as high. So 25 plus your 20 is 45. So it can go as high as 45 degrees and still be operating sufficiently, or it can go as low as 35 degrees and still be operating efficiently. In this case, it's at 40 degrees, which is midpoint. And as I say, the colder the air coming on, the lower my head pressure. The warmer the air coming on, the higher my head pressure. And that's the reason why when you get these condensers blocking up, so when you find that they're getting full of dust and dirt or whatever, there's no airflow going across, and that's why your head pressure increases. And that's why they go out on head pressure. And as soon as you clean that condenser and allow for airflow, then the head pressure will drop and everything starts working normally again. Does that answer your question?
Yes, it does, yeah. Hello.
Yeah, great. Okay.
Yes, thank you.
Okay, so, I know that I've thrown a lot at you today, and there are some videos out there. Again, what I've done is there's about a series of 10 videos. They're 10 minutes at a time. So, and again, I think Shane will send you the link if he hasn't already. And it'll explain how to measure subcooling, and it explains how to measure superheat, and it explains about delta T total, which is the total temperature difference between your air on and your refrigerant temperature, and that's for both on the evaporator heat exchanger or the heat absorbing heat exchanger, if you want to call it that, the indoor coil, whatever way you want to call it, and then the outdoor unit or the condensing unit. It's the principle is there. About it and that. So there's a couple of small 10-minute videos. We're going to cut this down. This is coming in at about with all the bits and pieces coming in at about an hour and a half, an hour and 40 minutes. So we're going to cut that down, and we'll make it a useful 40-minute video, so that you can go and play fast forward, reverse, and pause and all the rest to go through it. So I'm going to, unless you really want to continue, I'm going to maybe call it a night, unless there's some pressing issues. You're not expected to have this portfolio completed tonight. So in other words, we've done enough that you can go down as far as you can go start these 3 if you want. There are enough videos out there to help you using your dual menu thermometer calculate the following. So using the tools menu, click the thermometer button and calculate the following: evaporating temperature, superheat value, evaporator delta T, evaporator delta T total, condensing temperature, subcooling value, condenser delta T, and condenser delta T total. So delta T is temperature difference of the air on and air off across the evaporator. Delta T, temperature difference of the air on, air off across the condenser. Delta T total, difference between the refrigerant temperature circulating within the evaporator and the air coming onto the evaporator, or the room temperature if you like. And the same here with the condenser, delta T total, difference between the air coming onto the condenser and the temperature of the refrigerant circulating within the condenser. Subcooling value is the difference between your condensing temperature as read from your high side gauge or the middle of your condenser and the temperature of the refrigerant at the bottom of the condenser. In other words, the liquid temperature at the outlet of the condenser, so the liquid pipe leaving the condenser going towards the receiver. Difference between those two is your subcooling value. And remember, subcooling is a value, it's not a temperature, it's a value. And that value should be anywhere between 4 and 7 degrees of a difference. And the same with the superheat, it's the difference between the temperature at the outlet of your thermostatic expansion valve or the middle of your coil or the inlet of your coil, anywhere within the after the expansion valve device or after the metering device, and the temperature of the vapor where your bulb is clamped, where your thermostatic bulb is clamped, or as read from your low side pressure gauge. So the difference between those two is your superheat value, and that should be a difference of between 5 and 8 degrees. But you've enough to be going on with in terms of even just doing those first 3. And again, when you hand these up, you'll actually be handing these up on the last day, so on day 6 when you come back here. So don't be panicked if you don't have them all completed by then, because we'll have time to do it on the last day as well, and we'll kind of do a bit of peer-to-peer learning. So we'll work with each other, and you guys will teach each other and help each other and so on as well. So, but try and get as much of it done, and then we can tidy it up. But the idea is that you hand it up before we leave here. I already did this purge with you, so you can go through that yourselves. And I already did. Well, we didn't do that, but you can figure that one out yourselves. So you'll get through the leak detection. So we'll go through some of this a little bit more as well. So by the time we're finished, or by next week, I'll have the rest of them actually covered.